So, good morning, everyone. My name is Professor Richard Emsley from the University of Manchester, and it's been a great pleasure to serve as a programme chair for this year's Royal Statistical Society Annual Conference, and now to welcome you all here to the University of Manchester and to Manchester itself. So, we're going to get straight on with the programme and the first plenary session. We're delighted to welcome Professor Xiao-Li Meng from Harvard University. Professor Meng is Dean of Harvard University Graduate School of Arts and Sciences, the Whipple V. N. Jones Professor and former Chair of the Department of Statistics at Harvard. He received his Bachelor of Science in Mathematics from Fudan University and his PhD in Statistics from Harvard in 1990. And he was then on the faculty of the University of Chicago until 2001, when he returned to Harvard as Professor of Statistics. He's well known for the breadth and depth of his research, including theoretical foundations of statistical inference, quantifying ignorance via invariance principles, and applications in natural, social, medical sciences, and in engineering. He's also known for his innovation and passion about teaching, as well as his engaging and entertaining style as a speaker and writer. And so we're very much looking forward to his talk entitled Statistical Paradises and Paradoxes in Big Data.
Thank you for the very kind and generous introduction, which I wrote. It's such a great pleasure to be here, and thank you for such a great honor. And I know that some of us have been worried about the future of statistics, and probably more precisely the future of statistician. And I tend to be a little bit more optimistic, especially after having a cup of good glass of wine. What I have been thinking about is we're really what I call in the time of the statistical paradise. And I've been in this profession for 30 years. I started my PhD study at Harvard exactly 30 years ago. And I have to say that in the 30 years, as many of you know, that the field of statistics has changed so much. And we're really in a time where we have so much opportunities, but as well as we have some challenges. So what I'd like to share with you today is really both sort of my optimistic view about statistics, as well as some interesting challenges that we face and how far we can go to address them just by using very classic statistics. And so let me first say what I mean by, let's see if this works. What do I mean by paradise? Well, I guess for anyone, particularly teaching university, that the paradise is arriving when you see students are just coming to your field, the field of your interest. And as we all know that there has been such a growth of the students coming to statistics, particularly and at the undergraduate level. And what I want to emphasize is this, what I call the general pipeline. It's just not those students that we're trying to attract, but it's just generally students who have this great interest in statistics. At Harvard, when I was a department chair, started department chair, that was 2004, 2005, we had 5-6 students total in terms of the undergraduate concentration. It's a single digit. And by now, some of you may have heard that we have about 200. Now, as much as my ego would compel me to claim that was the leadership of my leadership skill, as you know well, that is happening everywhere else. That the growth of the number of students has been just tremendous. But the other indicator that we're really in a very good time is what I call that we now can have. Let's see if this thing. I have to get very close to this. We now can really have much better airplane, taxi, party conversations. As many of you must have experienced. By the way, I want to see a show of hand. How many of you are students or postdocs? Okay? So you may not have experienced this, but for many of other people, especially those who has as little hair as mine, you would know that any time when you mention, I'm a statistician, or I teach statistics, you know what's the response, right? The response is always like, oh, that's the most boring course I've taken. I hate it. I didn't do well, right? And so I found in old days that it was a very effective way for me to stop a conversation with someone sitting next to me by claiming, say, I'm a statistician. The only time that did not work was I was taking a taxi from the airport to Vancouver, the JSM that year. And once I mentioned I'm a statistician, the driver got very excited. He said, "Oh, I'm a mathematician." And it turned out to be true that he was actually some kind of part-time professor teaching at the Washington University, Seattle, but he was driving a taxi cab at Canada. I don't know what that says about American economy, but that's a different story. But most seriously, I think that this is really a golden era for us to do some serious foundational research. And I know many of us have been engaged in big data research, by which we probably do a lot of researches that including model building, model selection, large P, small n, all sorts of really interesting research. But what I want to emphasize today, and I'll share a little bit of the research I've been doing, is how we can really using deep statistical training to think about quite a few research problems that have really become so important because of the arriving of the big data. And particularly I want to talk about, and I'm not learning, clearly I'm not a good Bayesian. I should have stayed here, this side. I particularly want to talk about these three classes of problems that I called multi-resolution inference, multi-phase inference, and the multi-source inference. And I wrote them in this article for the COPS volume, and particularly this was written for the future statisticians because I list a bunch of problems I think we should try to solve them. So let me start by telling you how I thought about formulating this way. This was about 4 or 5 years ago. I was asked by the US Census Bureau to serve more or less like a statistical quality control person. They have had this project, a really large project. It's called On the Map. Now you can just Google On the Map. You will see that what they produce, and this is public available, is this sort of live data that you can zoom into any region, trying to study essentially this local employment dynamic. You're trying to study this is about the Las Vegas, who lives there, and where these employees work, where they live. So all sorts of these sort of local label dynamic information. And the idea here is that anyone want to study any region, at least in the US, you can zoom in, zoom out, and you can study all these relationships. Okay? And that is a humongous, a project. And it's obviously this is what I call multi-resolution, because simply there is this resolution. You're going out and back and forth, and hopefully whoever uses this data, they can make inference about any local dynamic, however local, however global they want to study. Is that clear? Okay. Now you may ask, how did they do it, and what are the data? Well, first I have to tell you that anytime you work on these projects, you face the issue of confidentiality. And this is not just about confidentiality of the individual workers, where they live. Nobody wants everybody to know where they live, where they work, how they travel, right? That's not somebody like to share this information, but most of us probably don't. But this is not just about the confidentiality about these individuals, there's also confidentiality for these companies involved. Okay, so what's interesting here is that all the data you will see online are not real data. All the data, they have a fancy term. Gosh, I keep forgetting. It's called, all the data they have, they're called synthetic data, which means that it's all simulated data, all right? What they did is they built this gigantic sort of Bayes machinery. And it's a very interesting way they did it. When I say they, it actually is led by economist John Abel, who become associate director of the Census Bureau now. They have lots of data sources I'm going to mention in a minute, and they use the privacy control. This is probably one of the most innovative ways of using a PRI. We typically use PRI to gather information. They use PRI to control privacy. So when the data set become too small, they were purposely putting the PRI to dilute the likelihood. Right? It's the opposite use of the, it's really quite interesting. way of using Pri. The reason I call it multi-phase is really because this is a type of data set. When a user uses it, most of them probably don't even realize none of the data are real. And obviously, whatever people have put in will have impact on your final inference. And whatever those people, Census Bureau people, when they're doing it, the data they have are not their own data. The data collected from all sources have been pre-processed by so many people. Okay, so this is a few years ago that I wrote an article with my wonderful student Alex Block, and now works for Google. We basically trying to set up a theoretical foundation about the pre-processing, which is complete a mess. Okay, you can see how hard it is. And later, my other student and I, we wrote another paper trying to use this multi-phase perspective, thinking about imputations. But that's not the focus of today's talk. Today's talk, I want to really focus on the multi-resolution and the multi-source problem. Let me emphasize what is the multi-source problem here for this particular data set. They used 20 data sources in this called the longitudinal employment household dynamic system. And I want to emphasize the variety of these data sources as well as the different quality here. They have survey samples. In this context, you probably should regard them as a golden standard because at least we have some control. This is survey samples. It's a monthly 60,000 household, but that only covers 0.05% of the U.S. population in terms of number of household. But this will be regarded as a good quality data because at least it's intended as a survey data. Then you have this administrative record. For example, they have unemployment insurance which covers in 90% of U.S. population. Well, that data was never collected, never intended for inference purpose. In fact, we know it's a biased sample. For example, all federal employees are explicitly excluded. Okay? But then you also have census data which covers 98% of the U.S. populations. So what you see here is you have a variety of data sources. They have very different size. Some only cover a tiny bit of a population, but presumably have good quality because they're survey data. And then their other data are collected for other purpose, but they covers a huge amount of, huge percentage of the population. Okay? So the question I was asked then was by Jeremy Wu, who then was the project manager of the Census Bureau project. And the point, I'm going to use that as my key point here. The multi-source problem here is really the issue of quantity versus the quality, right? Because the big data, as I just showed you, provide the opportunity to accumulate so many different data sets, but most of them are really not collected for the inference purpose. Now, the question Jeremy Wu asked me was the following. And he came to Harvard, gave a talk, and he specifically asked me the following question. He said, we know well by now that the 5% of random sample is better than the 5% of non-random sample in measurable ways, right? We know how to measure bias. We know how to measure predictive powers. We can do all those things. We have 100 years, theory, sample survey theory, other theory to say, what do we know about random sample, okay? The question he asked me, and this is exactly the question he asked, but is any 80% of non-random sample better than a 5% of random sample in measurable terms? What about 90%? What about 95%? What about 99%? Now, I want to see a show of hand here, okay? I want to ask you that if you are given a 5% random sample, we tell you that the random sample, you trust us, we have done a good job, then I also give you, say, let me pick up a 90%. 90% of population, I tell you it's a 90% population, but I have no idea how the sample was collected. Which of those you would trust more? How many of you raise hand for trusting the 5% random sample? God, this is a statistical conference, I can tell. How many of you will trust the 90% of the non-random sample? All right, there's a few brave souls. I assume the rest of you are falling asleep or... Great question. That's absolutely the key. You give the you give the punchline for my talk already, okay? The correct answer, now particular students should pay attention to this. The correct answer most time is it depends, okay? So actually, it depends on what we mean by non-random. Now, here's the problem. When you say something random, we understand. The general public thinks random is just something chaotic. And we understand what the random means, right? There's a probabilistic controlling mechanism, right? But when we say non-random, what does it mean? There's all sorts of ways to be non-random, right? And so the question is really, obviously if the 90% has some good way of measuring how random it is, it might be better. Now, not too long ago, Professor Kaiden and Louis asked the following question in their discussion papers last year's, was like 2 years ago at the JSN. They asked even a harder question. Which one should we trust more? A survey with 60% response rate or non-probabilistic data set covering 80% of the population? That is an even harder question, right? Because now the survey itself, it was intended to be a random sample, but unfortunately people choose to answer or not, so you have another issue come in, okay? So what I want to do today for the first half of the talk is really to convince you there is, I should have said I want to convince you that, first, this is a really hard question. But it turns out that there is a way to think about this, at least to make some comparisons by using incredibly simple statistics, okay? Or I should say, use incredibly simple sort of statistical formula. So this is what I want to convey today. Let me see if I can get the. I'm going to show you what I call a universal temporary, I call the Trill Identity, because I can't figure out the name for it yet, and you probably can suggest a better name for this. Okay, so what I'm going to tell you is this. I'm going to set everything in terms of finite populations. This is a tradition of the, for example, survey sample, but it's also really the realistic one to think about the current big data, like internet data, how people use it. Okay, suppose that I have a finite population, and here, let's say it's a United States population, which would be 320 million, and you are interested in estimate some average of a function, okay? Now, it looks like a very simple, but by choosing different functions, this covers really most of the survey estimate, okay? And what you have is a data set with unknown quality. Let's say you have a data set. This is the estimate. And I'm going to write the estimator using this little trick, which for anybody who have done finite sample calculations, you know this little trick. You write everything in terms of population value, but you introduce this RI equal to 1 if that particular subject is recorded, equal to 0 if it's not, okay? Now, I'm not making assumption these R's are random, because a lot of a lot of internet data, you have no idea whether they're random or not. And there are people who argue, say, I have nothing random, okay. So it doesn't matter whether it's random or not. What I can do is I can write this as this simple average, all right? Suppose like with unknown quality, whatever I have, and the most common estimated people using will be this simple average. Now, there's more fancy version. You can use weights, so on and so forth. But let's look at this very simple version, okay? Now, so what I want to study is the difference between this and this. At the first sight, I told myself, like, what can I do other than write down the difference, right? Because I'm making no assumption of anything. This is truly a non-parametric formula, okay? Because I'm not making an assumption about the yi's. Yi's here are fixed. These are finite sample calculation. Yi's are not, I'm not assuming any models. I'm not assuming anything about the I either, other than their 0, 1s, okay? But it turns out that you can go very far by rewrite this difference in the following way. Let me see. What I'm going to do is that it turned out that, since I'm taking average with respect to this index, although there's nothing random, I can rewrite this as a mean with respect to a uniform on the index. Is that clear? Because that's the only thing. That's just a mathematical trick, right? I'm rewriting this average as expectation with respect to this index, which takes 1 over capital N for any index. Is that clear? Okay, but that goes a long way, because once you write that, you see the difference between them is the average of the product divided by average of the R and minus this, right? Because this is just repeating. By taking the common denominator, you will see the numerator becomes what? Becomes the expectation of the product and the product of the expectation. What does it tell you? That's a covariance, right? Okay? Once you have the covariance, I can write that as a correlation. I can write that as a correlation between R and the G, and then, there's a standard deviation of the G, as well as the standard deviation of the R. But remember, R is a 0, 1. For 0, 1, the standard deviation is what? It's a Bernoulli, right? It's P times minus P, and the expectation of R is this fraction of how many sample you have. So if you do the calculation, you will get such a simple formula. So I'm going to spend really quite a few minutes on this formula, because I want convey to you that this formula tells us a lot about what we have been doing and the trade-off between data quality and the data quantity. But just to make sure that you will remember this formula, I'm going to adventure that I'm going to compare this formula to something that, for anybody who ever studied mathematics, there is this really famous, curious, and fascinating formula in mathematics, which contains 5 most basic numbers in mathematics, which is this. You guys remember this, right? This is always the most fascinating formula, because nobody knows what that really means, but you can verify it. It contains all these 5 fascinating mathematical symbols. So I'm going to venture to say, well, the formula I just present you actually contains the 5 most basic fundamental symbols in statistics: the mu, the sigma, the rho, the sample size, the population size. Okay? Now, the population size looks a little bit odd, because most time we tell our students, forget the population size. You only need to worry about the sample size. Ironically, because of big data, we now need to bring back the total, the population size. Okay? So now I'm going to tell you why I want you remember this formula, as much as like this curious one, because here's what's happening. These 3 quantities actually represent index 3 problems that will make the inference not accurate. One is the data quality. The correlation between the R and the value you record, that is the index how well you have selected your sample, right? Because, as you know, if any time a person responds or not depends on the values of their of their value, then there'll be induced some correlations, and that will induce bias. Okay, and then the variance itself, or the standard deviation, I call it's a problem difficult, because the more variability you have for the G's, the harder it is to estimate. If everybody gives the same answer, if everybody has the same value, you only need the one value to estimate the whole thing, right? Okay. What is this? This is simply the quantity. It's saying how much samples you have, right? So that's the data quantity instead of data quality. Now, the reason I write this way, and I call this sort of the trill, is because this formula tells you there are only 3 ways to reduce your errors. Okay? Improve the quality of your data, increase the size of your data, or reduce the difficulty of the problem. There are these 3 ways, only these 3 ways, to make the error as small as possible. What we have been doing for all these years, we are working on these 2, right? I'm going to show you in a minute what happens if you do, say, simple random sampling. What happens to that correlation? Simple random sampling, you will see the formula itself does not matter whether R is random or not. But once we do the probabilistic sampling, these R become random. And if you do well, you can make that R practically uncorrelated with any functions you want to measure. Okay, and obviously you can see that correlation on average is 0, if you do simple random sampling or any equal probability sampling. And I'm going to show you in a minute, it's not only the mean is 0, the variance is tiny for that correlation. So for years, what we do is all these probabilistic sampling is a very clever way to reduce this correlation, to make sure whatever people respond is uncorrelated with the values that they will report, okay? But this also says probabilistic sampling is one way to get what we want. There are other clever ways to reduce the correlation without doing probabilistic sampling. I'm going to say a little bit more later, okay? Now, how do you reduce that? Well, there are all sorts of ways, right? Using control variates, using stratification, right? Using all sorts of other things. By applying this formula to a specific subset, you do all those things, do regressions, right? This is all about to reduce the difficulty of the problem. Now the big data arrived, said, wait a minute, I have another way to make this small if I can get the little n as close to capital N as possible, right? That will make this small as well. That, at the beginning, you may think of that is really another paradise because we don't have to worry about difficulty of the problem. We don't have to worry about how to get the quality right. If we get enough data, we should be fine, okay? Very unfortunately, in order to make this thing small, you need enormous percentage of the population. Depends on the size of this quantity, okay? And I want to illustrate to you how small this, how tiny bit this might appear to actually really overwhelm what you think is the big data, is the benefit brought in by the big data. So to see that more clearly, I first want to, oh, by the way, this formula turned out that also has a great implication in the quasi-Monte Carlo literature because they have an inequality by bounding this one is between, less than 1, they have this famous Kusama-Hawak inequality, but now they can do the more refined version. So here is one insight that I did not have until I've done this calculation, and I surprised myself at the beginning. Remember, I defined the correlation between R, the indicator, as well as the G function, right? It turned out that if you're doing simple random sampling, you can calculate that, the variance of that quantity, the mean is 0, that's obvious. It turned out the variance of the correlation is 1 over capital N minus 1. Capital N here is a population size, okay? And this holds regardless which function you're looking at. So basically, the simple random sampling essentially eliminates that correlation for any G function you're looking at. And 1 of n, it could be incredibly small, right? Okay? But this also shows the trouble we have when we deal with a data set with unknown quality. Because the simple random sample allows we make inference only depends on the size of your sample because it theoretically guarantees the variance of the correlation is 1 over the population size. Once you don't have that, the population size comes back. So now let's look at what happens. So in a simple random sample case, that you will see you will put back into the formula, you will see the mean square error is of a very familiar form, right? It's the 1 minus, this is the finite sample correction, this is the sample size, and this is now you have to redefine, this is the population variance using 1 over capital N minus 1 instead of, this is 1 over N, and this actually provides another interpretation why we had to do N minus 1 instead of N. I'm not going to get into that. But the punchline here is that when you do probability sampling, it doesn't have to be simple random sampling. You could do other sampling. Equal probability will work as well. It's slightly different, but it will be at this rate. You pretty much get, you have the rate of going to 0, let's say mean square error, using with this rate, which is the sample size. The problem is once you get into big data with unknown quality, let's say there is a little bit of correlation between the way the data is recorded and the data itself, then what's happening is this becomes the dominant term. The variance for big data, there is one big benefit of the big data, is the variance is practically 0. You don't have to worry about the variance, okay? There's not much variability. But that correlation is going to stay, Okay? If the correlation state, you can see this mean square error goes down to 0, not as 1 of n, but rather at this 1 of minus the fraction. Unfortunately, this goes down to 0 much, much slower than this goes down to 0. Okay? Just as an illustration, let me do the following. I can equate the big data problem into a simple random sampling. I can equate this formula to say, if you give me a big data, and let's say I have some measure of the rho, what will be the equivalent effective sample size for that simple random sample? Okay? And the formula practically is equal to this. There's a little bit because of capital N, but if you just treat this as n, essentially you will see the effective sample size is governed by this quantity. The trouble is it's 1 over rho square. Okay? So if rho equal to 0, you effectively get infinite sample size. All right? But if the rho is even very tiny, so I'm going to just illustrate, just as an illustration, how striking this is in terms of treating quality for quantity for quality. So this rho or rho square, I haven't decided which one I should call it. I call it data defect index because that's all tells you the quality. Suppose rho equal to 0.05, okay? That's seemingly tiny. If there's a 5% correlation between the value recorded and how you record them, let's say Singapore recording is a response. Since I'm a little bit biased, I tend to report my income when it's low. If I have a 5% correlation, then you see that if I take half of the population, this is 1 over 0.05 squared, that's 400. That means that a half of population equivalent to only simple random sample size of 400. Now, you know how striking this is, because if I take the United States population, 320 million, half of the population is what? Is 160 million, right? It says that 160 million people, if I have the correlation seemingly tiny, 5% of correlation, that effectively the data quality is equivalent to a 400 simple random sampling. I just achieved a 99.999 some reduction of the sample size. Okay? Why it's so striking? 2 things. One is the simple random sampling knocked down that correlation into 1 over the population size. In order to get the population size, that's a much, much smaller ones, right? Okay? The second, what's the big trouble here? The big trouble is now the population size matters, not just the. So if you think that this is very striking, well, let's go to China. Then the half of the population is about 700 million, right? And you can make that as large as possible. Okay. So what are the lessons learned here? The lessons learned, first, what matters most is the quality, not really the quantity. Second, I should just stop walking. Watch the relative size, not the absolute size. The third, don't ignore seemingly tiny probability samples, right? In real life, if somebody study a population, say I have 160 million, people, let's say voting in the United States, right? That's the topic everybody's interested in these days, right? Now, and then you have like a simple random sample, 400. How many of the people will say, well, let's pay attention to the 400, ignore that, well, not ignore, at least, pay equal attention. That's very unlikely, right? And as I said, the goal here is really not necessarily doing probability sampling, but to ensure the correlation as small as possible, to ensure that when people respond or when you record these data, there's no sort of systematic sort of this correlation. That correlation essentially is a measure of the bias. And I mentioned previously, say, probability sampling is not the only way of doing it. It's a great way of doing it, if we can, but if you can have clever ways to get people to answer answer you when they're not thinking why they answer. There are these behavioral scientists or psychologists. They design these very clever surveys. Inside the survey, they have put in these hidden checking points to make sure that your answer is reliable. And you can imagine when you have lots of data, you build those in, you potentially can eliminate lots of data using that hidden check. Only retain some small portion, you may still bet off because the trade-off here is really tremendous. Okay. So there are really all sorts of implications. What's the next implications? As I said, public sampling is extremely powerful too. This one really reminds me how powerful, we know that, but still I have to do the calculation. So how powerful it is to think of something simple random sampling can knock down that correlation into 1 over, capital N. And there are many other lessons that I don't have time to get on. For example, this formula also has implications when you think about confidentiality, when you start putting randomness into the data and how that, you can mess up with things, but how can you balance that? Now, as I said, I call this talk Statistical Paradise and the Paradox, so I do want to say what's the paradox here. The first paradox, and you're probably not familiar because I coined this term, I'm calling it the big data paradox. Okay, because why? I said the big data, what's the punchline here? Well, let's look at what happens if we did not realize this problem. Because we know the difference between them, remember the formula was exact, in terms of effective sample size is far, far larger than if you are just blindly putting, let's say you put 160 million data points, think about that is your size. If you're forming a confidence interval using that seemingly real sample size but not the real one, let's say 160 million, what's going to happen is you have an interval with incredibly tiny width and centered at the wrong place. What does that guarantee? You guarantee yourself will never cover the right thing, right? In fact, the only way you can cover it is if you have a gross overestimation of the variance, or you use a ridiculously large multiplier. Remember people talk about 6 sigma? Here you need a 600 sigma in order to, and in fact, to be exact, it's 632, if you can do the calculation, okay? Either you have to rely on that your variance estimate is 300 times more, ridiculously overestimating, or you use some ridiculous multiplier that your interval will never cover, right? Because you're centered in the wrong place, and you insure yourself such a tiny one. So the paradox, I want to use it, really saying, the bigger the data, the sure we will miss our target. Now, the reason I use the phrase, obviously, this is not real paradox. This is the paradox in the sense, the Simpson paradox, which is the next topic I'm going to talk about. But I want to just sort of emphasize this is the type of thing that people will miss if they don't think it in a statistical way. All right, so this is really the first part of my talk. And now, any questions so far? Well, I was waiting for someone jumping on me and say, Xiao-Li, you're stupid. Big data is not about population inference. Big data is about individualization. It's about predicting individuals, right? Because everything I talk about was about population inference, okay? But I hope you also, even you don't care about population inference, by going through that, you realize how important the data quality is. Don't be impressed by this enormous number. I can easily translate it into simple random sample. 400 is not that impressive. 160 million seems very impressive. They're exactly mathematically quantifiable, the same quality, okay? With a seemingly tiny 0.05 correlations. So now let me switch to the part that many of you probably care more, is about this individualization, okay? And this part is actually joint work with my wonderful student, Kelly Liu, and I didn't know that he actually showed up right there. That I didn't know he would be in this meeting. It's great, Kelly. So any question I cannot answer, you ask Kelly. So what does big data promise, right? The big data promise that they can help us to look, each of us, or whatever we look at, in a much more a high resolution. That's where the resolution comes in. And there's all sorts of things called personalized medicine, education, news, marketing, you name it. But there's not really a sort of free lunch here, right? So I've been using this phrase, say personalized treatment sounds heavenly, but where else did they find the guinea pig for me? Because none of us, well, I should say, every one of us is unique, hopefully. right? So how did they find the data? How did they test something on somebody else and claim that it works for me? So the curse is no one is perfect like you. Now, of course, some of you may say, Xiao-Li, that's a rhetorical question because nobody takes personalized very seriously in a sense that it's completely personalized. We always stop somewhere, right? Then, of course, my question is where? Where's the boundary? How do you decide when to stop, right? And what's the statistical theory to sort of deal with that, right? Okay. So this is, as I said, these are the work with John work with Kelly, and I'm going to now talk about really a well-known paradox called the Simpson paradox, and you may not see the connection immediately, but I hope that in a few minutes you will see why it's so important for us to think about the Simpson's paradox here. So I want to show you this data set, and some of you might be familiar with it. I think I'll be using this data set. I give many talks using the same data set. This was published in the British Medical Journal in 1986, exactly 30 years ago. And it's a study about kidney stone treatment. Now, how many of you suffer kidney stones? You know what I'm talking about, right? Extremely painful. Okay, don't have it, extreme painful. So this particular paper, if you only read the abstract, and most doctors only read the abstract, okay? You will find it claims that the treatment, it compares two treatment A with treatment B, and treatment B has 83%, and treatment A has success rate of 78% treating kidney stones. I have a question for you. If that's all the data you have, which treatment will you choose? Come on, that's not a trick question. But if you're suffering the kidney stone, you want to have something. Now, you guys are too sophisticated, okay? If that's all the data you have, which one are you going to take? B, because if you take A, the stone is in your brain, right? It's not in your kidney. Why would you take A when the data shows that the one has a more successful rate? But since we're statisticians, we actually read the paper. Once you read the paper, somewhere in the paper, which is not explicit, but you can go, you can find in the paper that you will find out information that when you divide them into these two different sizes, then suddenly treatment A is better, right? Okay. Now, I actually use this example to teach my students. I'll be teasing the students, say why the reasons, we can have a great discussion, why it's important to give the fractions, not just give the percentages, because they give you a lot more information. You see the confounding, so on and so forth. But for this group, we don't have to talk about that. But you all understand this is what? This is a Simpson paradox, right? Okay. Now, what's the real problem here is clearly this was not a clinical trial, even 350, because treatment A is applied mostly to the largest stone, and it turned out that treatment A is the open surgery, that's why it's applied to large stone, and treatment B is this unpronounceable treatment. Do we have a doctor here? I don't know how to pronounce this. Okay. Now, you see how dangerous this is, right? Because this article was trying to promote this so-called non-invasive surgery. If a doctor only read the abstract, it's a non-invasive surgery, has a better rate, why not take it, right? When you read the article itself, you will get sort of a different answer. And the real problem here is here why is cure not cure, and the problem is it's not a clinical trial, and the axis here is the pre-treatment stone size. Now, of course, there's a really harder question, right? The harder question is how do we know the answer will not flip if I further divide? Okay, that is where the big data comes in. This is tiny data, but the principle is exactly the same. What the big data allows to do is go deeper, stratify, go all sorts, what I call multi-resolution. You think about zooming. But at which level you're going to stop that give you the right answer? And how do we even quantify it? How do we know that's even the right answer? Okay, so just to see, I know this audience is incredibly sophisticated, so I'm going to give you a test. Okay, this one is just known as the Simpson paradox. Now I'm going to use exactly the same data, but I'm going to change the story a little bit. Okay? Instead of treating the kidney stone, now I'm going to take the same data set, pretend it's a clinical trial, but this time it's a clinical trial on helping ease the pain instead of treating the kidney stone. And this time, the stone size will be post-treatment measurement. Okay? Is that clear? All right. So now, exactly the same data set. All right? Y indicates the pain relief or persistence. X indicates the post-treatment stone size. Let's say we have two treatments. A is a control treatment, which is known to have no effect on stone size, let's say Tylenol. B is this experiment treatment, which we don't know whether it has effect on stone size or not. Okay? Now you are given exactly the same data set, and you are in pain because you're suffering the kidney stone. Okay? I want you to make a decision now. All right? So now we tell you this was a clinical trial. Okay? And so this is, in the general population, when they aggregate, you get this data. Otherwise, if you want to stratify, you get that. But now the stone size itself is a post-treatment. If that's all the data you have, which treatment are you going to take for yourself if you suffer a large stone? That's all the data you have. Okay? Well, let's look at what are the possible options here, right? And how we're going to analyze this data. You carry a large stone, which should move, right? Think carefully, okay? You're in great pain, okay? So there is one answer I can give, what Kelly and I, we've been calling as resolution 0, meaning because we're not using the size of your stone as a predictor, okay? Think about the more covariates you use is the higher resolution you're going down, going deep, okay? So you can certainly using this. You say, well, I don't know, I don't trust the stone size because it's a post-treatment stone size, so I may as well ignore that information. So in that case, you would take treatment B, right? Think about yourself, ignore the size of your stone, then you become, without the information, you'll be using that, okay? Now, somebody may say, well, no, wait a minute. I know my size, I know my stone size is large, so can I use this one? Well, it's a little bit tricky because you can trust the 73% because we know the treatment has no effect on the stone size. So you know that's a post-stone size is also pre-treatment stone size. But I have no idea who are these people. What I want to compare are the people, how the drug works on people who have large stones before the treatment, right? Because what if the drug, unlikely, but what if the drug actually increases the stone size? Well, at least that's a theoretical possibility, right? So that would be another answer possible. Let me see a sort of show of hand. How many of you would prefer this argument, therefore taking treatment B? 2, 3, okay, 5, okay, it's a single digits, all right? How many of you will take this argument and then take treatment A? There are more, okay, almost tripled. I hope the rest of you have not fallen asleep. What are other alternatives here? Since many people have not answered, not like the first question, right? Many people answered. This one seems a little bit trickier, okay? So now let me propose a third answer and see if I can convince you, okay? What about I use the following argument? I say, look, in the treatment A, I trust this number, right? Because, that's using my condition and it's all valid. And the treatment B, I don't trust this one, but I trust this one, right? Because that one I know it's valid. So how about we do something like this? How do I make comparison to this? Well, Kelly and I, we've been calling this called a cross-resolution comparison. We call it 0.5 because this is a resolution 1, condition on the stone size, this one doesn't. So if I make the comparison, I will be using this, but actually will be saying the treatment B is 10% better instead of only 5% better. Looks the conclusion seems even stronger. How many of you would like to use this cross one?
I would want to know more about kidney stones.
You want to know about kidney stones? You should talk to a doctor, and we can have a good glass of wine. I tell you my own suffering experience. So I see a few people raise their hand, okay? Now, this seems a little bit odd, particularly if you haven't studied statistics, you might jump on this one. I probably can convince the doctor. I'm using the best information and each treatment. But statistician might say, wait a minute, you're comparing two very different. You're comparing a marginal estimator with a conditional estimator. What are you doing, right? Okay, let me give you a little bit of background. Now I'm going to tell you a little bit how I'm thinking about this problem, what I call the multi-resolution problem. Okay, so what we're trying to do here. The game here, the whole game of an individualized treatment is no longer about collecting a bunch of people to make an inference about population. It's rather, say, finding a group of people to approximate me. Okay? It's a very different game. Right? So the idea here is I want to know how I would respond or how you would respond to these two treatments, and if I giving you either both of them, but that's never going to happen before you actually get treated, right? The data we have is we have data of some people get treated by treatment A or some people treatment B, and none of them was treated by both of them, right? So this is the whole, well-known sort of clinical trial setting, and it goes to all these counterfactual, setup, right? So the strategy is I need to identify a population that is relevant to me. So the question is how relevant is relevant? Should I take all the people who have the large stone size? Probably I should, but the large stone size should be what? Should be pre-treatment instead of post-treatment. Okay, so the question is how do you formulate this relevant population, right? So the way you can think about it is, say, suppose there are some intrinsic characteristics. For example, how you respond to each treatment. That is intrinsic characteristics, right? You can think the conceptual even before you've given the person a treatment. You can think about how this person is going to respond to A or respond to B. And what you want is to match all the people who share these characteristics, right? Okay, so how many things you want to match? We use the concept called the resolution, but you can just think about here simply how many covariates you use. The reason I used this resolution idea was actually really inspired by this waveless literature, which actually was many years ago. Guys in the audience that kind of remembered how I get into this wavelets research, but I find that it's very inspiring to think about, like, you zoom into each individuals, and you decide at which level you're going to ignore their sort of individual characteristics. So literally, for those who are familiar with the wavelets literature, these are like a wavelets coefficient. This is just a schematic sort of a representation. You can imagine that each of us, you have lots of low resolution characteristics, high resolution ones, and there's some other individuals. What you want to find is to decide, because you don't want to match every single detail. Everyone's is unique. If you match every single details, you end up with just yourself. That's not fun, okay? So you want to define literally using the term primary resolution. You say, well, it's good enough. I only want to match people who are the male or same age, so on, so on and so forth. Okay. So then ignore the rest. All right. So the idea of this sort of component, common resolution, you want the estimate to be the common resolution, but for the estimate itself, you could do a Biasvariance trade-off to use the cross resolution ones. So the idea here is, say, if you want to estimate that treatment effect and treatment and the outcome and the treatment A, you only have these people who were given that treatment A, and then similarly, if you want to do the treatment B, you only have those from given the treatment B. Although this is what you want to compare, but you may have these samples which has different different subpopulations. Now, because of different subpopulation, you will include some bias. But remember, there's a bias-variance trade-off here. What is a bias-variance trade-off? It's a very simple one, right? Because as I find people more and more like me, what's going to happen? The available pool becomes smaller and smaller. The bias is smaller, but the variance goes up. If I relax this matching criteria, the variance goes down because I have more people, but the bias may go up because it becomes less relevant. So this cross sort of a resolution estimator is really the idea of trading the bias, trading the bias for variance reduction. Okay, so there is a condition that Kelly and I derived. It's a little bit hard to explain, but essentially it's saying this mixed resolution estimator can have smaller mean square errors than the common resolution one, which had to be necessarily low resolution, that if only if the cross treatment predictive information, meaning how much I know about this treatment predicted the other one, that the missing information is less than 50% of the observed within treatment predicted information. It's a little bit hard, it's even mouthful to sort of explain this, but the detail is in the paper. So goes back here that we will see that in this particular case, that because the time is going to run a little bit fast, that this cross term ones is actually really sort of a closer to the middle for all the possible range. In this particular case, if you ignore the sampling variability, you can really actually you can really show that the possible range in the B is actually outperforming A that always. So this one actually, the cross one is really, it's an indication that it's really a better ones. So now let me just say very quickly in the negative 2 minutes I have, how do you set up this whole multi-resolution idea? The idea here is that if you do this prediction, let's say you have lots of covariates, right? These days we talk large p, small n. We typically put down something called a signal and a noise, but in reality, this epsilon contains both the unmodeled signal as well as the intrinsic noise, right? So, and then the signal noise are really relative concept, because signal for one study can be noise, for another, and vice versa. So how do you model these? How do you think about this sort of information accumulation? What you think about is, let's think about you have, let's say, sigma field generated by a bunch of covariates. Suppose you have infinite many covariates. Think about that as your resolution level, and you can let's look at the conditional mean at each resolution level is your signal, and the variance is your noise. And then there's a very simple ANOVA decomposition you can write down. Basically, it tells you the variance at a resolution R is equals to the variance at any high resolution as well as the difference between them, right? So from that, you're basically saying that anytime when you look at the conditional variance, anytime you look at the variance, there's really no such thing as a pure variance. The variance is all caused by the difference among these resolutions that you forgot to take into account in your model. The only time you really have a pure variance is that even you look at a person in terms of infinite detail, it's still possible, at least in theory. You can never prove this wrong. This depends on whether you take a deterministic view of the world or the stochastic view of the world. Even you know everything about a person, the outcome of the treatment could still be random. And so this quantity itself, you can set a zero if you believe the world is deterministic, or you can leave it there, okay? So the whole game of this multi-resolution inference is to model this sort of total resolution bias and to see how it goes down as the resolution goes up. So in a nutshell, what we have here is, say, you want to predict an individual, and what we're doing here is we actually have three types of errors. You set up a resolution level. That was essentially is a model selection error, because you want to use infinite, but you can't. But once you set the level, you still need to estimate all the estimations, right? But then you even you have done everything, infinite information, you may still have the intrinsic errors there. So there are these three levels of the errors. Okay. So the holy grail here is really how do you decide the right level of the stratification, or I call the depth of the inference, how deep you want to go when you have all these big data. So this essentially is equivalent to the bias-variance trade-off, but hopefully the resolution framework suggests some new strategy assumptions, for example, that a cross-resolution estimator. So for those who just woke up, let me summarize what I what I talk about. I talk about these two use of big data. One's for population inference, one is for the individualized prediction. For the first one, I emphasize data quality is far more important than the data quantity. The second, the probabilistic sampling, is extremely powerful, but it's not the only strategy to achieve good quality. The third is that it's not the big data, big absolute size is a big fraction. Rather, it's a huge fraction you will need to overcome these sort of these quality issues. In terms of individualized inference, we're changing the game. It's about approximating the individuals by a proxy population. And the key is here to define the proper level of the approximation by the Biasvariance trade-off. And finally, the concept of bias is really more critical than pure variance, because essentially there's no such thing as really the variance. It's all because we have forget to include all these biases at the different resolution levels. Let me leave with you a puzzle, or rather a quick question. Which city is running faster with big data? Because since this Manchester is known as the 2016, the European City of Science, I thought it'd be fun to pose a question. It's not a Manchester, that'd be too obvious. All right, tease you. I don't have time to tease you because I'm already in the negative time. Do you recognize what? This is actually from Chicago. It's kind of very impressive. They put the big data on, is this a bus or this is a subway? This looks like a subway. So when I saw this is from Sandy Zabel, someone you recognize him. The point I want to make is that we're really in a paradise when you see like big data is even on a subway. There's something right about it. But in order to keep this paradise as gained and we never lose it, I think that I do want to sort of emphasize how important for all of us to not only communicate our statistics well to the general public, but also collectively do a much better job in terms of teaching statistics. And I think particularly at the very elementary level. So in the future, you won't run into people who say, oh, I absolutely hated that. This is how we have been getting these reactions. So I'm very pleased to see in this particular conference that we actually have multiple sessions on communicating statistics as well as teaching statistics. To a plug, I will be talking another one this afternoon for the significance session. And I know there's Thursday morning, there's a session on communicating statistics, particularly with the teaching at the very elementary level. And I want to say that for us to really keep our paradise, that I think probably the most important for us to convey is not just because there is a job in statistics. These days, a lot of students come in because there's a job. What we should convey is really the joy of the statistics. It's how much fun it is to do statistics intellectually and personally. And I thank you again for giving me the chance to share with you some joy I had with statistics. Thank you very much.